Hello and welcome to our presentation on nuclear recommendations. Currently, about 30 countries worldwide are operating nuclear reactors. These reactors are supplying 12% of the world's electricity. As of 2018, countries worldwide are operating 450 nuclear reactors for electricity generation, with a combined electrical capacity of 394 gigawatts. There are also 50 nuclear power reactors under construction with a combined capacity of 63 gigawatts and 154 reactors planned with a combined capacity of 157 gigawatts.
There are some problems in the process of energy generation. For example, transportation. Transporting nuclear waste from power plants will lead to some problems. For example, if there is a slight knock or even crash, accidents on the transportation of radioactive material could cause the contents to spill and affect a wide place. Despite all the cautions that are put into the place when transporting nuclear waste, accidents can still occur and have a devastating effect on those crashed. People who work around nuclear materials exposed to large amounts of radiation. Improperly stored waste at a nuclear site can also lead to the levels of exposure that are beyond what is acceptable for humans. Radioactive waste is an inevitable byproduct of the application of ionizing radiation. In most countries, all short-lived, low or intermediate level nuclear waste are disposed of using surface or underground so as to maintain the safety for people, but these waste maintain their radioactivity. For the third problem, the disposal of nuclear waste is the hardest materials on animals and plants' life. Accidents can happen and least even though the waste is well sealed inside huge drums of steel and concrete. Nuclear waste can have drastically bad effects on life and cause the growth and to give huge environmental impacts that can harm many millions of animals and species.
Due to the above problems, we have some recommendation in the following four aspects: generation efficiency, operation safety, waste disposal, and public attitudes. Let's start with generation efficiency. Thorium as a nuclear fuel might be the advancement of nuclear power generation. Thorium is another antennae to space lighter compared to uranium. It is not laterally fertile, but it is fertile upon absorption of neutron. It decays into plutonium-233 and then into uranium-233, which is an excellent fissile fill material. It is better than uranium-235 and plutonium-239 as it absorbs fewer neutrons, which lead to better neutron economy and, more importantly, on average, thorium cycles exclusively allowed thermal breeder reactors. Uranium-233 produces slightly more than 2 neutrons per split, even when it is split by slow-moving neutron. That means it's possible to breed new uranium-233 from thorium in a thermal reactor. There are many advantages when thorium is used instead of uranium. First, thorium is much more highly concentrated, meaning it takes less work to extract the same amount of energy generating potential during the mining process. Meanwhile, thorium is more abundant in the Earth's crust than uranium. There are 3 times more thorium than uranium in the Earth's crust. And in terms of energy production, 1 ton of thorium is approximately equal to 200 tons of uranium and almost 4 million tons of coal. This is due to the improved efficiency and recycling properties of a thorium reactor. Second, let's talk about operation safety. Again, with the use of thorium, nuclear might drop the dangerous tag and just be clean. Thorium may revolutionize the world. A liquid fluoride thorium reactor is a type of molten salt reactor, significantly safer than a typical nuclear reactor. It's used a combination of thorium and fluoride salt to power a reactor. First, thorium-233 and uranium-233 are added to fluoride salt in the reactor core. As fission occurs, heat and neutrons are released from the core and absorbed by the surrounding salt. This created a uranium-233 isotope. As the thorium-233 takes on an addition neutron, the salt melts into a molten state, which runs a heat exchanger, heating an insert gas such as helium, which drives a turbine to generate electricity. The radiated salt floats into a post-processing plant, which separates the uranium from the salt. The uranium is then sent back to the core to start the fission process again. The uranium and thorium can either be mixed together or separated with a thorium blanket surrounding the uranium core. In either case, the molten salt containing the uranium also transports heat out of the core to secondary circuits that ultimately power turbine. The actual fusion only happens in the reactor core because that's where the moderator slows down the neutron to make fission much more likely. In this case, the moderator is a lattice of graphite channels through which the fluid flows. Graphite is particularly great because it slows down neutrons without absorbing them. When the fluid is away from the graphite, neutrons speed up, which means fission slows down. As it is in liquid form, the fuel can be quickly drained out from the reactor in emergencies. A plug with a low melting point will melt if the core gets too hot. The fuel then drains into a tank where fission is impossible. The liquid fuel becomes less fissile as temperature increases with the appropriate building weights. So even if every mechanical or human mechanism failed, the reactor would simply power down, which can highly prevent accidents happening.
The solution for the radioactive waste disposal. The radioactive waste is stored in underground repositories nowadays. However, organizations such as Greenpeace has pointed to several risks, not at least of which being the chance of the toxic materials seeping into the groundwater or a fire releasing radioactive gases. 90% of total radioactive waste are conditioned and stored in facilities isolated from the environment by specially engineered barriers. However, from a sustainable development perspective, it is a serious problem to solve the waste to future generations. We can know that temporary storage is not a good solution. Nuclear power could become increasingly important as the world continues to combat climate change. Nuclear is dangerous for many years to come, no matter where we store it. The most hazardous waste, uranium-235, has a radioactive half-life for more than 24,000 years. So these materials won't be safe for millions of years. How can we deal with the waste? Nobel laureate Gerard Morrow is finding out an interesting solution, where it may be possible to transmute nuclear waste into a safer form in the future. Morrow and Donald Strickland invented a process called triple pulse amplification (CPA) at the Laboratory for Laser Energetics at the University of Rochester. CPA creates very short laser pulses but with ultra-high intensity. The original research actually focused on applications like laser machining and eye surgery, but Moran said CPA could have a use in processing nuclear waste too. Currently, CPA can produce laser pulses as brief as 1 attosecond. That's a billionth of a second. As Morrow stated, if the pulse rate is increased by roughly 10,000 times, nuclear waste might be transmuted into something safe if the speed is fast enough. With an ultra-fast laser pulse, it may be possible to bombard nuclear waste and knock protons out of the nucleus. That turns a dangerous substance like uranium-235 into something harmless like lead. So, as a result, the problem of the waste disposal, we hope, can be solved in the future by the new technologies and inventions. For the public attitudes, people may concern whether nuclear power is safe enough and concern about the radiation. In order to raise positive attitudes towards the nuclear plants, a recognized need for a greater electrical supply, maintaining the safe operation of existing nuclear plants and informing the public, providing the opportunity for meaningful public participation in nuclear plants issues are necessary. For earning the public acceptance and trust, the governments in the regulatory area should maintain high standards of safety, while ensuring the regulation is effective, focused on the real risk and compatible with the regulatory approach for other energy sources and industrial activities. The governments and regulators have to design something so as to encourage public processes for the setting and the environmental assessment of the waste repositories, provides adequate opportunities for public to participate in and to develop the criteria for the waste management facilities. As a result, the processes for decisions should incorporate the best scientific information as well as the broad spectrum of public views. Governments should ensure the public can continue to access the basic information about the energy. As a result, the governments should look to the future contribution from nuclear energy and to ensure the regulation is prepared to deal with the issues of refurbishment, uprating, life extension, and decommissioning of existing reactors, so as well as new creator designs.
This is the end of our presentation. Thank you for your time.